So for this one, it's talking about the permeability of free space, mu naught. You can find it experimentally by measuring the magnetic field by a current carrying wire at various distances. The variable is linked by the equation. Now, this equation is essentially B equals mu naught I over 2 pi, that right, times by 1 over R, which is of the sort Y equals mx plus C. So the first part says just complete the table above. Easy 2 marks. Sorry, 1 mark. 1 mark is something this easy. You just go 1 divided by 2.0 by 10 to the negative 5. That gives you 100. Next one gives you 50. Next one gives you 33 and a third. Next one gives you 25. And next one gives you 20. So there's 1 mark. You then had to graph that and include a title and appropriate axis labels with units. So the next page, to save a bit of time, I've already done it. So I've gone magnetic field versus the inverse of the distance away, 1 over R. I've included the scale here by 10 to the negative 5. I've also included magnetic field with its unit. And then down the bottom, I've written down the scale, 1 over R, and it's per metre. Notice I've started the axis at 0. I've kept my scale consistent each time. I've also utilised these bold lines just to make life easier, because every one of those individual lighter lines is, well, they're worth 2. So you just count by 2s, 2, 4, 6, 8. And then going up here, if that one's 0.4, then 1, 2, 3, 4, 5. That one there's 0.2. Okay, just pick a scale that's easy for you. You don't have to use the entire graph. I'll just move it a little bit so we can see the whole thing. And you'll also notice that I've already picked up that one of these points is an outlier, 6.7 by 10 to the negative 5 and 33. So it's way up here. So quite obviously, it's no good to us. Okay. You'll notice I've also used the broken symbol or just 2 straight lines. So yeah, if you're not starting at 0, you should be putting those in to let us know, because an axis is just a number line. All right, so from there, I've graphed 100 and 2 by 10 to the negative 5. So that's this one here. Then I've gone for the 50 and the 1 by 10 to the negative 5, and you can see that looks fairly linear. So the next part says draw in a line of best fit. So we'll see how I go with this one. Line of best fit sort of goes something like that, just pretty damn straight, provided we ignore this outlier, because that outlier we need to comment on and say, well, that's a mistake. So determine the gradient of the line of this best fit. So the gradient of the line is, if you remember our formula, you can use Y2 minus Y1 over X2 minus X1, or simply rise over run. So let's have a look. We'll take this one here, which was 100 across, comma 2 by 10 to the negative 5. We'll use those two. Now, it doesn't really matter where else you use, provided I always look for where it's going to hit nicely. So here's another nice one, goes straight through that one. So let's go 20, comma 0.4 by 10 to the negative 5. Now, it doesn't matter where you use it from. I just select the easiest ones to get values from. So with that in mind, we now go down and we go Y2 is 2 by 10 to the negative 5 minus 0.4 by 10 to the negative 5 over 100 minus 20, and that gives me 2 by 10 to the negative 7. as my gradient. Next part says, now that's not going to be the perfect gradient. You will have multiple gradients there, just depending on where you've drawn your line of best fit and how well you've drawn it. So just going to enlarge that a little bit more. Use this gradient to determine the permeability of free space. So before I told you that magnetic field is equal to mu naught I over 2 pi r, which means that magnetic field is equal to mu naught I over 2 pi times by 1 over r, which is what we've just graphed. So that means that this section here must be our gradient. So that means that mu naught I over 2 pi must equal 2 by 10 to the negative 7. So rearranging that, we were also told that current equals 5 amps. So that gives us 5 mu naught over 2 pi equals 2 by 10 to the negative 7. Multiply both sides by 2 pi and then divide by 5. And that will give you with mu naught equals 2.5 by 10 to the power of negative 7. And that's our estimate for the gradient of, for the permeability of free space. Righto. As you can see from your line of best fit, does not fit perfectly through all data points. What is one reason why, in terms of error or uncertainty, this would be the case, and justify your answer? So we've got a couple of things. We've got an outlier, and if it's included, changes our line of best fit, and of course our gradient, which is often called just the M value. So if you include that, that can modify your gradient, and also the line of best fit may be out as it's done by eye, not using stats, because if we're doing stats, it'll be at least squares regression fit. So one reason why in terms of error, or in terms of this would be the case, so outline, yep, I'm comfortable with that. Compare this to the accepted value of mu naught. Now, on your table for mu naught, can't remember what the value for mu naught is. So the value for mu naught from your data sheets is 4 pi by 10 to the negative 7, which looks a little bit deceptive. If we actually calculate that, it is 1.26 by 10 to the negative 6, and we got, what was our value? 2.5 by 10 to the negative 7. And our M was 2.5 by 10 to the negative 7. So you can see we're actually a factor of 10 out. So comment on any discrepancies. So that's a compare, the comment out by a factor of 10. Now, suggestions for this, there could be lots. Our line of best fit gradient is not exact. Such small values of measurements rely heavily on the equipment used. There's 2. Could be anything as long as it was reasonable and justifiable. And that would have given you your 2 marks.